Hi, what I'm going to do is I'm going to take Newton's laws and I'm going to apply it to two-dimensional forces, okay? Because not everything's always in a straight line. And so we want to talk about things at angles and so forth. Well, linear or angled, we can always use this same approach. Let me draw something. I'm not even going to talk about what it is. Let me just say we've got something like this, and we've got a force like this, and we've got a force like this. Now, normally when you're doing a free body diagram, you'd label all the forces. So this is a free body diagram. Okay, let me give you some numbers. Let's say 40 newtons and 25 newtons to the right, and let's say this is also 40 newtons, and its angle of, I'm going to change that just a tiny bit. I just want that angle not to be 45. I'm going to make that angle 30 degrees and 40 newtons. Okay, and when we draw our free body diagrams, we always want to make sure the vectors are kind of close to scale. So maybe I need to draw that a little longer. In other words, this vector and that vector should be the same length if they represent the same number of newtons. So what we then do, that's the first step, is free body diagram. Second step is to declare a frame of reference and break the vector into those components that fit in the frame of reference. Well, I'm just going to there's no other reason for me to do it a different way. When we get to things like inclined planes, things going down a ramp, the accelerations down the ramp, we're going to have our frame of reference like this. But for this situation, not knowing anything about it, this could be a top-down. I'm looking down on somebody pulling this way and that way. So I'm just going to say, I'm going to take the easy way out, and I'm going to say, okay, I'm going to make my frame of reference just like this, okay? So step one, free body diagram. Step two is to make sure you find out how much each force is pushing in each dimension of the frame of reference. So 25 newtons, no problem. Oh, and by the way, I got to pick positive directions. I'm just going to pick positive that way and positive that way. Two dimensions, two positive directions. So I sometimes say that's the free body diagram. This is the frame of reference, FOR. And what I'm going to do is take, well, the 40 Newton one, that has no problems. That's still right along one of my axes. So I'm okay with that. I don't have to change that at all. 25 Newton one is also along one of the axes. I don't have to break that one up at all. 25 newtons. But the 40 Newton one is not along the axis, so I have to break that into components. How much of that is pulling up, and how much of that is pulling to the left? So what I will do is I will take my calculator, which I've left over there, and I know that 40 times the sine of 30 will give me the opposite, which is the vertical. 40 times the sine of 30 is 20 newtons. And I should be able to do the other one, but I'm feeling weak. I think it's 34 point something. 40 cosine of 30 is going to be 34.6 newtons. So 34.6 newtons this way. Okay? So, free body diagram, frame of reference. When I say frame of reference, I mean you select a frame of reference, select two orthogonal or perpendicular axes, pick positive directions, and then decompose. In other words, find the components of the angled forces and replace the angled force with this. Now, on an AP test or exam, this is the free body diagram. This is not. This is a representation of the free body diagram of the forces Okay, how much is pushing? This is a means of solving the problem. But if they ask for a free body diagram, give them this. Okay. Another thing is on the free body diagram, don't break it up right there. I mean, you might be able to use that, but these are the only real, true forces. Okay. So now we come over here. We've got our frame of reference. Now we're set, and we can do our Newton's second laws. And our Newton's second laws are going to look like this. What I'm going to do is two laws. I'm going to do a vertical and a horizontal. And I'm going to call that the y, and I'm going to call that the x. So I'm going to say sum of forces in the x direction is going to be equal to the mass times the acceleration in the x direction. Sum of forces in the y direction is going to be equal to the mass times the acceleration in the y direction. Okay, and now all I have to do is substitute these in, and I can solve for what I'm looking for. If they gave me the accelerations, I could use the forces and the acceleration to solve for the mass. Okay, but much more commonly you have the mass. I'm going to give you a mass here. I'm going to pretend this is, I don't even know. I'm going to pretend that the mass is 4 kilograms. M equals 4 kilograms. I'm making this problem up. I can choose anything I want. But in a problem, you would generally know it. If this were vertical and horizontal instead of maybe looking down on it, this would typically be mg. Okay? So let's see. Okay, so this is not going to be like a vertical horizontal. I'm looking down on this thing. But let's just say the mass. Let me change it. I'm sorry. Let me change that because I don't want it to look like that. I'm going to call it 6 kilograms. I'm pretending I'm looking down. Somebody's pulling this way, somebody's pulling this way, somebody's pulling this way. I want to find out how it's going to move. So in the horizontal direction now, the force, the sum of forces is going to be positive 25 plus negative 34.6. So 25 plus a negative 34.6 equals the mass, which is 6, times the horizontal acceleration. Well, that's not too bad. So I do 25 minus 34.6 is going to end up being negative 9.6. And so negative 9.6 is the net force, what we call the net force horizontally. How much more it's pushing one way than another way. 9.6 newtons more this direction than that direction. Okay? Divided by 6, and it should be 1.6 in the negative direction. Negative 1.6 meters per second squared. So there's our horizontal acceleration. It's going to accelerate 1.6 meters per second squared this way. We don't know anything about how fast it's going, by the way. I don't know anything about this problem other than the free body diagram. It doesn't tell me velocity. But I do know it's going to accelerate in this direction. If it were moving in that direction, it would slow down because the acceleration is to the left. Okay, then we do the y. 20 minus 40. 20 is positive plus negative 40. 20 minus 40 equals 6 times the vertical, or excuse me, the y acceleration. Negative 20 equals 6a. I'm going to check to make sure. Yes, I think you can see that. And then 20 divided by 6 ends up being 3.3 bar meters per second in the negative direction is the y acceleration. So that is the bulk of what we got. We can combine those two. Negative 1.6 meters per second squared and negative 3.3 meters per second squared. We can combine those doing Pythagorean theorem, and the actual acceleration would be, and this should be repeating down there, Pythagorean theorem would tell me that it's actually an acceleration of 3.697, well, it's probably 3.7 meters per second squared, and the direction would be given by the inverse tangent of this over this. I'm not going to sweat that right now. Big thing for this lesson is I just want you to understand these are the steps. Free body diagram, frame of reference, 2 Newton's second law equations. I have a t-shirt that says that. Free body diagram, frame of reference, in other words, break the angled vectors into the correct perpendicular vectors, and then just do 2 Newton's second law equations. Okay, and when you solve that, you'll be able to solve the whole problem. And I think if you keep this in mind, boom, 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 it's trivial.